Okay, first problem on page 4, page 4 of assignment 4 is to use induction to show this statement that 2 to the 2n minus 1 plus 3 to the 2n minus 1 is divisible by 5. So again, we'll just do the inductive step. So we're going to be allowed to use the fact that 2 to the 2k minus 1 plus 3 to the 2k minus 1 is divisible by 5. And we're going to want to use that in order to create a statement that makes it appear that the same quantity with k replaced with k plus 1 will work. So we'll notice that 2 times 2k plus 1 minus 1 plus 3 2k plus 1 minus 1. That's the quantity we're going to be working with. So first of all, let's simplify. That become a 2k plus 2 minus 1. So I'll write that as 2k minus 1 plus 2. And this one is 3 to the 2k minus 1 plus 2. My motivation for keeping the minus 1 and moving the 2 over here is that I do want 2k minus 1 and 2k minus 1 as my exponents. So by exponent rules now, right, the x to the n times the x to the m, I can separate this into the 2 to the 2k minus 1 multiplied by 2 squared. In other words, this becomes 4 times 2 to the 2k minus 1. And similarly over here, this will become a 3 squared, or a 9 multiplied by 3 to the 2k minus 1. Okay, now here's where the genius step comes in. Remember, this is what I want, and this is what I have. So to make that happen, I'm going to take the first part and write it down. I wish I had this. So in order to motivate to get that, the problem is I have the 2 to the 2k minus 1, but there's a 4 out in front of it. So what I'm going to do is I'm going to add 4 times 3 to the 2k minus 1. Because what that's going to do is it's going to allow me to factor out the 4, and then I'll have the actual quantity I want. But I can't just go adding stuff like that in unless I also compensate by subtracting it. So I'm going to have to subtract that. And don't forget, I still had this little bit on the end. 9 times 3 to the 2k minus 1. But what's genius is, now look what we've got, right? Now we have from here 4 multiplied by 2 to the 2k minus 1 plus 3 to the 2k minus 1. And that part we're happy with, right? Because we knew that 2 to the k minus 1 plus 3 to the 2k minus 1 was already divisible by 5. So this is definitely divisible by 5. On the other hand, we have these two pieces, but notice that they have a common 3 to the 2k minus 1, and what's left is a negative 4 plus a 9, which is a 5. So this part is also divisible by 5, because you can actually see the factor of 5. And of course, if you take a multiple of 5 plus a multiple of 5, you get a multiple of 5. So that finishes the problem. That finishes the inductive step for us. On the right, we have rewriting in sigma notation. So let's be nice here. We're going to add up k equals, you can see that these are squares, right? 1 squared, 2 squared, 3 squared, all the way up until 6 squared. So we'll do k equals 1 to 6, and we'll add up the k squareds. So that is all they wanted us to do here, to rewrite in sigma notation. Below, we have solve the equation. So this one's going to be a logarithm type problem, right? Because it's exponential and we have to use logs to undo it. Base is 3 and base is 2, so I'm not going to be able to do much for fun here. So I'm just going to ln both sides right off the bat. I'm going to take a logarithm of both sides. The log of a product becomes a sum. So on this side, it'll be ln of 5 plus, also exponents come out in front, so I can say x ln 3. And on this side, it would become an ln of 7 plus an x minus 1, exponent out in front, ln of 2. Okay, let's distribute first. ln 5 plus x ln 3 equals ln 7 plus x ln 2 minus ln 2. Okay, I'll collect the pieces with x's over here. So x ln 3 minus x ln 2. And I'll collect everything else over on this sid. ln ln7 minus ln2, and then I'll move the ln5 over. So it looks like after I factor out the x, what I'll be left with here is a numerator of ln7 minus ln2 minus ln5 over this, which is ln3 minus ln of 2. You could do some simplification here, but the problem doesn't ask it for, so don't do more than you need to. Okay, and then for the purposes of making this answer key, I'm just going to do this one in the calculator and figure out what that is. So we need to see x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60. And so if I graph this just in standard window, -10 to 10, I can see that there's a root that seems to be around -2 and seems to be around 3, and that would be consistent with the rational roots test. So I'm pretty happy with that. We'll go with that. So let's see what we end up getting. We're trying to find all the zeros. I think those are zeros, but let's make sure. Does -2 as a root go into 1, -3, 6, 2, -60? The answer is 1, -2, -5, 10, 16, -32, -30, 60. Yes, it does. Whoops. And then let's go see if 3 goes in. And so 1, 3, -2, -6, 10, 30. Yes, it does. And so we end up getting the root, or let's factor this now. So f of x looks like it's going to be an x plus 2 times an x minus 3, x plus 2 from here, x minus 3 from here, and then our residual, which is x squared minus 2x plus 10. Let me take a couple seconds out, and I can't factor that nicely. So we'll just break out the quadratic formula. A equals 1, b equals -2, c equals 10. So the discriminant is b squared, which is 4, minus 4 times 10 times 1, so minus 40, which is -36. So it looks like the roots will be, what are the zeros of the function? There's a 0 at -2, at 3, and then from here it would be -b plus or minus the square root of -36 all over 2 times 1. So it looks like 1 plus or minus 3i are our last two zeros.